The LR circuit without battery obviously behaves very similar to the LR circuit with a battery, but the difference in it is in kind of how you get it going. First, you have to have the LR circuit with a battery. And so you can see I've got the switch here. So what you would do is you would actually close the switch and you would leave it closed for a little while, and so you would get a current going. And then you would suddenly flip the switch over to here, and you do it essentially immediately, instantaneously fast, so that the current, there's no break in the current, so that it's still flowing. Right? If you don't do that, if you just connect right here and there's no current to begin with, well, there's not going to be any current at all. Nothing interesting happens. You have to have some current to begin with. So usually, again, start by hooking up to the battery and then flip the switch right over so you have some initial current. And what's going to happen is, of course, there's no battery, so that means the current is going to decay. Now, if there was no inductor, it would go to zero right away. The resistor isn't going to do anything to keep the current going. It's just going to go to zero right away. So what would that look like? It would look like this. If I had let it go, say it started at 9, and then if I only have a resistor, I suddenly flip the switch, there's no inductor, well then guess what? It just goes right down to zero. It would just drop to zero. But if you do have an inductor, it's going to resist this change. And what you're actually going to get is exponential decay. And so that's going to look like this. We're going to have exponential decay. Let's say we start at 9 amps. Oops. It's going to look something like that. And the reason it's going to look like something like this is because the inductor won't let the current change all at once. It won't just let it go immediately to zero. It resists the change in the current. That's what the inductor does. And so you get this exponential decay. It can't prevent it from changing completely, but it can alter the rate at which it changes, which is what happens. And so if we look at the formula, it's just exponential decay. And of course, we've seen this before in the RC circuit. Here, for the LR circuit, tau is L over R, the inductance over the resistance. And if T equals tau at that moment, then what we get is I equals I initial. That's e to the negative 1. Okay. E to the negative 1 is approximately 0.368. So it's approximately 0.368 of the initial current. So in my example, I said my initial current was 9 amps. Okay, so 3.3. Now each one of these tick marks is 0.6. So this would be 3, 3.6, 4.2, 4.8, 5.4, and then 6. So 3.6, 3.3 is in the middle. So I would go over like so, and that seems to be right on this line. And so for this example that I've drawn, tau is approximately 5 seconds. This is how we read the time constant off of the graph. It's a nice, straightforward way to do it. And you want to be able to do that because, of course, we can do our calculations. We can go through and do the calculations to get tau, and that's important. But this is a nice, if you have the graph, it's a nice, easy way to quickly check your answer. And sometimes in some of the problems, you are asked to actually read the graph, not do any calculations, but read the graph and figure out what tau is. But this is basically all there is to the LR circuit. I did want to mention, I didn't mention this in the previous video, but I wanted to mention that you could analyze this with the loop rule. You could do the loop rule here, and the loop rule would certainly does apply. The problem is at the level we're at, you can't do much more because we're not using calculus. You can write down the loop rule and it's true, and then that's the end of your analysis. Basically, you can't take it any further. And again, that's because you really need calculus to go further than that.